Okay, so we arrive at the last theorem for this part of the course about compactness. Again, we have the space of continuous functions from a compact metric space K to a complete metric space Z, and we know that this expression here, D sub C, defines a metric on C, which turns into a complete metric space. In general, it's not a compact metric space. As we saw, in general, it doesn't have this Hein-Borel property whereby all closed and bounded subsets are compact. What we know is what we know about every metric space, right? So if I want to know whether a subset of C is compact, what I need it to be is closed and totally bounded. Right, closed, we know what it means. It means that, it's if you take limits of sequences of functions in there that converge according to this norm, the limit's still in the set. But totally bounded is different. And there's this very important theorem, Arzela Ascoli, that tells us when a subset of C, the space of functions, is totally bounded. So in order for it to be totally bounded, it's necessary and sufficient that it has two properties. First of all, it needs to be equicontinuous. And what does that mean? You remember uniform continuity, right? So I give you an F, I give you an epsilon. You have to find me a delta such that if I take any 2 points in the domain at distance less than delta, the values of F at these points are a distance less than epsilon. Equicontinuity means that not only that each individual function is uniformly continuous, which we have for free, right? So all functions in C are uniformly continuous. We also have this very strong property that I can choose the same epsilon. I can choose, given epsilon, I can choose the same delta for all functions f and all points t and t prime at distance less than delta. So it's a step forward. It's one more step from uniform continuity. It's kind of uniform continuity over the choice of function as well. Okay, that's item A. Item B is being pointwise totally bounded. What does it mean, right? So for each point in the domain, I have these points in the counter domain, right? There's a subset of Z, which I just compute f of t for all f in my family of functions, my collection of functions. And I want these sets to be totally bounded for all t in K. That's what being pointwise totally bounded means. Okay, so let me say it again. So there are these two conditions here, and they tell me whether a subset of the space of continuous functions, a set of functions, is totally bounded or not under this metric. These are equicontinuity, which is like uniform continuity that's also uniform with the choice of function in the family, and pointwise total boundedness. So just to mention, when the color domain Z is either R or RD, then this condition of asking that this is totally bounded is the same as asking that the set is bounded, right? So we know that in RD, bounded sets are totally bounded and vice versa. So, but for geometric spaces, this is what we can do. We need this pointwise total boundedness. And what is this anyway, right? So total boundedness means that you have finite epsilon covers where epsilon net for epsilon. It means also that the largest epsilon packing in the space, the largest set of points at distance greater than epsilon from one another, has finite size for any epsilon. And okay, and that's what, now we're going to prove this theorem. It's an if and only if, but I'm only going to prove the harder direction, which is to say, if F satisfies these two properties, then it has to be totally bounded. Okay, how do we do this? It's so how do we prove that something's totally bounded? I'm gonna take a packing in the set. So it's a family of functions in P that whenever different, they are at distance greater than epsilon from one another. And my claim is that the size of P is finite. It has to be finite. Okay? Right, so why does that imply what I need, right? So one of the things that we saw is that if a set is not totally bounded, then it contains an infinite separated set, an infinite packing inside it for some positive epsilon. Here, of course, epsilon is arbitrary. So I'm going to prove that whenever I have an epsilon packing, it has to be finite. Therefore, there's no infinite epsilon packing. Therefore, F is totally bounded, right? That's what I want to prove. But of course, at this point, there doesn't seem to be much that I can do. However, there is something clever that we can do here. And, okay, how do we put it? I need to prove that this is finite. So what I'm going to reduce, what I'm going to show is that if, that's step one, I'm going to turn this into a finite problem in some sense. I'm going to show that there exists a set of k points in K such that for all f and g in my family, they're different. The distance, the maximum distance between f of ti and g of ti for I going from 1 to k, that's at least epsilon over 2. Okay, so I'm going to finitarize my problem. I'm going to take, this is a problem of functions. The domain here is probably infinite, or kind of the hardest case is when it's infinite. But it doesn't. What I'm going to argue is that it doesn't really matter because of this very strong property of equicontinuity. I can find a finite family of points that sort of attests the fact that these functions have a big distance between them. Remember that distance from f to g is greater than epsilon. Whenever that's the case, I'm going to be able to find points t sub I such that at least at one of these points, the distance between f and g is at least epsilon over 2. So what that will mean is that these vectors, right, so for each f and p, I have a vector of these values, f of ti, which belongs to the Cartesian product of zt1 up to ztk, right? So the first coordinate of this vector is an element of what? What is the set? You remember, this is a set of the values of f of t1 as f ranges are over our family. So the values of ft1 belongs to zt1, the value of ft2 belongs to zt2, and etc. Okay, so this is a mapping that takes p, that takes an element of p, a function, and maps to a vector in this space. And we're going to argue that this guy here is totally bounded. Remember, there are assumptions that the individual factors are totally bounded. We need to put a norm over this product here, or a metric over this product. But once we do that, this is going to be totally bounded. Now notice the following. So this packing here induces a packing in this totally bounded space. And why is that? Well, because as we noted, right? So, I mean, that's, how do we play, what's the metric that we put over here, right? So if I take two vectors in this space, I'm going to use this max norm, this max metric, sorry. And this is z here. And there's not k, right? This is z because these functions take values in z. So I'm going to argue that this set with this metric is totally bounded. And once I have that, I'm done. Why? Because my epsilon packing in the space of functions gives me an epsilon over 2 packing in the space of vectors. And I know that all packings in the space of vectors are finite because this is a totally bounded space. Therefore, my original packing has to be finite as well. Okay? So that's the scheme of the proof. So just have to carry through these 2 steps and then we'll be done. Okay. Right. So how do we prove that there is this choice of points such that this holds, right? Well, we're going to use uniform continuity, or not, we're going to use equicontinuity. So we know there exists a delta such that for all t and t prime and k, if the distance between t and t prime is less than delta, the distance between the values of f, z, f, t, f of t prime, less than epsilon, for all f in my family. That's what continuity means, right? I'm just restating the definition here. Now, okay. So we have this delta, and actually let me make this epsilon over 4, right? It doesn't make a difference. This is just a positive number. For each positive number, I can find a delta. We're going to see why epsilon over 4 in a moment. Okay. Now remember that k is compact, therefore it's totally bounded. So I'm just going to write this over here. That k is a union of a finite number of open balls or closed balls, it doesn't really matter, around some points t sub I. So okay, if I want, since my definition of totally bounded has closed balls here, I can take closed balls of radius delta over 2, but then the open balls of radius delta cover everything. Right, so by continuity there exists this delta. And now, if I take f and g distinct in my packing, I know that the distance between them, well, the distance is a soup, right? But the soup is achieved somewhere because we proved that this is a continuous function. We actually argued that in the previous video that the soup is achieved somewhere. So this is d sub z f of t plus the g of t plus for some t plus. And now I notice that t plus has to belong to one of these balls, right? So I can just say, well, this is just distance of z of f of ti, g of t sub I. Sorry, let me put this like this. And then I have to pay a price because I move from t plus to t sub I. I move from t plus to t sub I. What is the price I pay? Well, by our choice of delta, so t plus belongs to the ball of radius delta around ti. So moving from t plus to ti has cost less than delta. And I know that when I change a point by less than delta, I change the value of the function by less than epsilon over 4 for any function in my family. And this is where equicontinuity is being used. I have the same delta working for all functions in my family. Therefore, for any functions in the packing, the price I go for t plus to ti is an epsilon over 4. Then I have another epsilon over 4 here. So epsilon over 2. And now what? Well, for these guys in the packing, I know that this distance is less than epsilon, right? What did I argue? I argued that there is a choice of t sub I. Take the t sub I such that t plus belongs to the ball of around t sub I. For this choice of t sub I, the distance between f t sub I, g t sub I, is at least epsilon minus this epsilon over 2. And that's what I wanted from before. I wanted to say that there's a finite collection of points in K such that for any two guys in the packing, the maximum of these values, distance of ft sub I, gt sub I, is at least epsilon over 2. And what I did was just that. I found one choice of y for which this is larger than epsilon over 2. Okay? Right, so this is what I wanted to achieve. So I finitized the problem. Okay. And now I'm going to do step 2. Let me okay. So right. So I'm gonna define the space, and here I put a metric. Right. The elements of this guy are vectors. The first coordinate is et1, kth coordinate is eti. The distance between two such vectors is equal by definition to max 1 over less than I less than k. Distance in z, right? All these guys are contained in z between zi and zi prime. It's an exercise to show that that's a metric. Actually, you've probably done this exercise by now. I honestly don't remember. And now, my point is that I argued that I have this map that takes an element of the packing and takes it to a vector. So let me call this M, okay? Just to give a name to the set. Right? And that what we argue is that if I take distinct element of the set, they're mapped to guys at distance, right? So distinct guys with the packing, you have distance epsilon, therefore their images have distance at least epsilon over 2. So, okay, because distinct guys are mapped to distinct guys, so the cardinality of P, if it's finite or infinite, doesn't matter, is the same as psi of P. And moreover, psi of P is an epsilon over 2 packing in M, according to this metric. Okay, now as I said, in order to finish, it suffices to prove that M is totally bounded. Because if I prove that, I know that the cardinality of psi of P, which is exactly the cardinality of P, is less than the packing number of M epsilon over 2, which is finite, right? That if M is totally bounded. And if this is true, then P is finite too. And now we're going to prove that this is the case, that M is indeed totally bounded. And notice that when we do that, we actually get estimates for the covering numbers or the packing numbers of this original family of functions. I mean, we're not going to work that out, but you could, in principle, if you want to get a very explicit proof, you could say, okay, if I know the covering numbers of ZT1 and ZTK, or the packing numbers, whatever, I can get a bound on the packing numbers of this family F, and therefore on the covering numbers as well. And that's kind of interesting, okay? But here's, okay, now we're going to just say, okay, my packing of unknown size in the space of functions became a packing, an epsilon over 2 packing in this space M of unknown size, and now I'm going to argue that the size has to be finite by showing that M is totally bounded. And how do we do that? So the claim is that M with this infinity bound is totally bounded. How do we prove that? Well, for each I know that ZTI is totally bounded. So there exists a family of elements that I'm going to call Zij, j equals 1 with some size M sub I, such that for all Zi and Zti, there exists a Zij from this family here with distance from Zi, so this is in Z, this is less than epsilon, well, over less than R. So I'm going to show that the R covering number, I'm proving here that the R covering number is finite, right? So I'm going to use covering instead of packing because it's slightly simpler for all R greater than 0. So what I'm saying is that because the set is totally bounded, it has a finite R net for any R positive that I choose. And this is my R net. So let me actually call this the R net for factor I. So R sub I, let me write it like this. So for all R, there exists an R sub I contained in Z, such that for all Zi and Zti, there exists an element of this net, a Z tilde I and R sub I, such that the distance in Z between Z sub I tilde is less or equal to R. That's a little R net. But this is my assumption. I want to argue that M is totally bounded. And I mean, the important thing is that this is finite. So how do I do that? I need to find an R net for this guy, right? That's what I want. I want a finite R net for this guy. And what I'm going to say is simply that if I take the net for ZT1, the net for ZT2, up to the net for ZTK, this is an R net for M. And how do I do that? How do I know that? Right, okay, if this is true, then I'm done, right? Because I have finite sets, or Cartesian product is also finite, therefore I've managed to find an R net for M, where R is an arbitrary positive number. By definition, a space is totally bounded if it has finite R nets for all R. How do I know this is an R net? Okay, take a vector Zi, Z1 up to Zi in this set M, right? By assumption, I know that I can match it with coordinates, right? I know that the first coordinate Z1 is R close to some point of the net R1. I know that the second coordinate Z2 is close to some point in the second net R2. And that's the same up to RK. So I can find, right? So if I look at this, these guys are in the R net, right? So they're in this guy here. And that's going to be, well, the maximum of D, Zi, Z, Zi, Z tilde I. But I've chosen these guys so that these numbers are all less or equal to R. So the maximum is also less or equal to R. What am I saying? I'm simply saying that if I have an R net for each one of these sets, then the Cartesian product with this sup metric, this maximal metric, also has a finite R net, which is just the Cartesian product of the nets. And with that, I've proven that for all R, right, I'm assuming these guys are totally bounded, so there are finite R nets for all R. My conclusion is that M is also totally bounded, because for all R, I can find a finite R net, just by taking R nets for the individual factors and taking the Cartesian product. Okay, so what have I shown? I have shown that this is a totally bounded space, therefore it cannot contain an infinite packing. And therefore the image of this packing P in the space of functions that's contained in the space cannot be infinite. Why? Because the image of this epsilon packing is an epsilon over 2 packing here. The space is totally bounded, therefore epsilon over 2 packings have to be finite, and therefore P has to be finite, which is what we wanted to prove. And with this, I finished the proof of Arzela Ascoli. Well, for us, perhaps it's interesting just because we've been talking about compactness, and now we have a criterion for compactness in the space of continuous functions. But this theorem is also useful for many things, including proofs of existence of solutions to ODEs by Euler's method. But we'll leave that for some other time. Let me just give you a hint of how you prove that if a set of functions is totally bounded, then it's equicontinuous and ZTI is totally bounded. Well, I mean, there are different ways of doing it. My favorite way of this, okay, I'm going to say this, pointwise total boundedness is not hard to prove. As I said, a function is totally bounded. Pointwise total boundedness is really not hard. But why is it equicontinuous? So I have my set F here of functions. And I know that I can cover it, so, and I want to prove it's equicontinuous, right? So so it's sort of the other direction. Given epsilon, want delta over 0 such that for all f in my family, for all t and t prime and k, if t and t prime are distance less than delta, then distance of f of t prime less than epsilon. I want to prove that that is true. So what do? All I know is that f is totally bounded, right? So I'm going to just cover it by very small balls, a finite number of them. So f is contained in a union of a finite number of balls. And the important thing is that I take their radii small enough. So I'm going to take epsilon over 4. And notice that in principle, it's hard to find this delta that works for all f. But there exists a delta such that for all f sub I, for all I here, I have this sort of inequality. Epsilon over 2 actually will work. And how do I know that? Well, okay, for each I know that f sub I is not only continuous but equicontinuous because k is compact. Therefore, I know that I can find a delta for any epsilon over 2, doesn't matter. But now there are finitely many functions, right? So for each one of them, I have a delta, delta 1, delta 2, up to delta m. If I take the smallest of those, then I guarantee this is true for all f sub i's. But why does that solve my problem? Well, it's really simple. Now, if you look at this thing here, distance of f of t to f of t prime, this is at most distance, well, say f is in this ball. Here's f sub I. Now I look at f sub I of t prime. And what's the price I pay to move? Well, I have to compute the distance from f to f sub I. And that's at most epsilon over 4, right? This ball has radius epsilon over 4. And then another epsilon over 4. And this guy here, well, if I assume this is less than epsilon over 2, therefore everything here, well, this is strictly less, right? Because this distance from f sub I to f is less than epsilon over 4. Therefore, what I just wrote is less than or equal to epsilon. And I've achieved my result. So by taking a delta that works for all set f sub I in this cover for this set f of functions, I have a delta that works for all functions. Well, all I need to do is to take a smaller value of epsilon here to make everything work. And that's it. So that's my hint. Thank you.